Hello, boys and girls. We are going to start looking at how we find terms of recursively written sequences. Lindsay, Luke, and Sarah created the following patterns. For each person's pattern, draw the next figure in the set. So for the first pattern, it's Lindsay's. How many blocks would there be in size 4? I'm sorry, I'm not going to draw it, but I could count the boxes and see that there are 3 here. There are 6 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you see the pattern that you're adding 3, the fourth one would be 12. The fifth one would be 15. The 10th one, so that's 5, 6, 7, 8, 9, 10. So 18, 21, 24, 27, 30. When we describe the pattern in words, we say that what it starts with, then increases by 3. Next one, Luke's pattern. Let's count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17. So here it starts at 5 and is increasing by 6. So the fourth one would be 6 more, so 23. The fifth one would be 6 more, 29. That's the fifth one. 6, 7, 8, 9, 10. So now we're adding 6. So if I add 6, I get 35, 41, 47, 53, adding 6, 59, and that's it. So it starts at 5, then increases by 6. So recursive sequences are always described by where they start and what happens to get from one term to the next term. How many yellow triangles in size 4? So I've got 1, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what would happen at 4? Here, I can't do increasing because it would be increasing by 2 and then increasing by 6, but I could times by 3 and find that pattern. If I times by 3 again, I'll get 27. So the fourth one's 27. If I times by 3 again, I'll get 81. And for the 10th one, I don't really feel like doing that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep multiplying by 3, describing the pattern. We start at 1 and multiply by 3. So how are Lindsay and Luke's patterns different from Sarah's triangle pattern? Lindsay and Luke were both adding objects. Sarah was multiplying. So remembering back to the intro from today, when you're adding, that's our arithmetic sequences. And multiplying, this is our geometric sequences. So if we remember it like that, what we talked about today, it would be easier to find the 10th object without having to go from each number to its next one. So the most complicated part when it comes to recursive sequences is the notation. And we use subscripts a lot in the notations from last unit, which I'm hoping will help. It's all about the subscripts not having meaning in what we're going to do, but it has meaning in what it represents. So if we have a sub n being the first term, okay, if a sub n is the first term, I'm supposed to write what comes next. The next term is going to have a subscript of n plus 1. Okay, for instance, if the first one has a subscript of 3, the next one's going to have a subscript of 3 plus 1, which would be a sub 4. So you don't actually have to add the 1. This would just mean a sub n plus 1 is the number that comes after whatever a sub n is. In the next example, if we start with a sub n minus 1, the term after that, if I add 1 to this subscript, your next subscript is going to be n. And if you have a term a sub n plus 8, what would come after that? Instead of being n plus 8, the subscript would be whatever that is, plus 1 more, which would be a sub n minus 9. So that's when they use subscripts. The next side is function notation for the same thing. So if the first term in a sequence is f of n, the next term would be f of n plus 1 more than that. If the first term is f of n minus 1, the next input would be n, because n is the number after n minus 1. And what would be after n plus 13, what would come next, would be n minus 12. So you add 1 to the subscript, in this case, or we add 1 to the input, if it's function notation versus subscripts. Okay, I believe this is note card number 62. I'm going to pause and finish this video and start a new one for what comes after. Okay, arithmetic sequences add the same number repeatedly. Common difference is notated with a D. So you get D by taking any term and subtracting the previous term. So if you're talking about a recursive formula, the a sub n, usually, there are other ways, but usually we start with a sub 1 being the first term, and then the next term is how I would represent a sub n, is going to be the previous term plus d. So anytime I'm given a recursive formula, it's always going to be next equals. Whatever they have in the first spot is the next term. And whatever they have in the formula is referring to the term before it, the previous term. So let's write a recursive formula here. To go from 2 to 5, 5 to 8, and 8 to 11, we're adding 3. So how would I write a recursive formula for that? I would say that the first term is 2. The next term is the previous term plus 3. This would generate this sequence. If it were geometric, instead of having a common difference, we have a common ratio. So get R by taking any term and divide the previous term. So to go from 50 to 10 and then 10 to 2, I could say, all right, R is equal to 10 divided by 50, which is 1/5. It's going to be the same thing if I do 2 divided by 10. You'd get 2 over 10, which is also 1/5, and so on. So that's our R. Our first term is 50. Our next term is whatever the previous term was times 1/5. So I could just put the 1/5 in the front, or I could have put times 1/5 at the end. Okay? This recursive sequence would generate that number. You could write and use a combination of operations. So timesing 4 wouldn't work here. Adding 6, no. So for this one, I would have to figure out a combination to go from here to here. So let's say if I times by 2, that would give me 4, and then I would have to add 4 to get 8. If I times by 2, I'd get 16. If I add 4, it won't give me 26, so that doesn't work. Let's see, times 3, I get 6, and then I would have to add 2 to get 8. If I times 3 from 8, I get 24, plus 2, I get 26. If I times by 3 here, I get 78, and if I add 2, I get 80. So just by guessing and checking is literally what I just did. I realized we have to times by 3, then add 2. So how am I going to write that as a sequence? The first number is 2. The next number is 3 times the previous number plus 2. So this recursive formula would generate this sequence. And now this last box shows them giving it to us as a recursive formula and asking us to find. So if they give us that the first term is 2, then I'm going to rewrite the recursive formula using next equals -4 times, so a sub n is next, a sub n minus 1 is the previous term. So -4 times the previous term plus 5. They want us to find the fourth term. You cannot go straight to the fourth term with recursive formulas. Here, I get the first term. The second term, I'm going to do -4 times what we just got there, plus 5, which is going to give me -3. Then, to get the next term would be a sub 3. To get that, I'm going to take -4 times this last term, and then plus 5, and that's going to give me 12 plus 5, which is 17. Now I can get the fourth term. I'm going to still have the -4. I'm still going to have the plus 5, but this 17, which was the previous term, is going to be what I multiply, and that's going to give me 68 plus 5, which is 73. So this is the fourth term. Okay, when you finish copying this, put this into your flip books. I want you to keep them up to date. This, I believe, is 62. I'm going to go check.